Hello, Math 30-1. Let's start things off by talking about how dumb I am. All right, so let's scroll our way up to yesterday's lesson where I made a mess of things. Not this question, but this question. Where is it? Oh my goodness, why don't I see it? It's the one that goes, oh yeah, there we go. It is this one. Thanks to our good friend Jared Han, who was like, hey, Mr. Kennedy, you made a mistake. And then I told him, no, I didn't make a mistake, Jared. And he was like, oh, okay. And he just ignored me and let me live my life. I did screw up here. So I had another student, shout out to Matthew, who was like, Mr. Kennedy, no, you definitely made a mistake. And then I was like, oh, I'm stupid. And I owe Jared an apology. I'm sorry, Jared. I'll never do that to you ever again. I can't believe myself. You're smarter than I am. I should know better. You're right. I'm wrong. There. We said it. It's over with. Okay. I made a mistake down here where I circled in green. Hopefully you caught it. 2 squared plus 7 squared does not equal 56. At least not in any country that I've ever lived in. It should have been equal to 53. And then you wouldn't have had to do all this crazy simplifying stuff. So it would have actually made the question slightly easier. But you know what? It's good for you. So, that's all it was. I was just trying to make things good for you and make you work a little harder. So I do apologize for that if you noticed that yesterday and you thought I was crazy. Now it's confirmed. Today, let's confirm I'm crazier. Let's try to make 0 trigonometric ratio mistakes. We're going to continue on with what we were doing yesterday, basically building triangles, learning definitions. We're just going to do it in more places. So yesterday we just did it in quadrant 1. Now we're going to kind of move around the map. So a little review, what we did yesterday. We learned 2 main definitions. There was something called a reference angle and something called a standard position angle. Those are probably the 2 most important definitions that you're going to run into. So the reference angle for an angle in standard position is the angle between the terminal arm. So that's our line that comes out of the origin, our terminal arm. And because it's the reference angle, we go from the terminal arm to the closest x-axis. Okay, that's a reference angle. So for instance, it's telling me right now, draw a 30-degree reference angle. Well, I could draw a 30-degree reference angle right here. That is a 30-degree reference angle because the distance or the angle between the nearest x-axis and the terminal arm is 30 degrees. But that's not the only reference angle of 30 degrees. I could also do a reference angle of 30 degrees over here. Like that. And that is also a reference angle of 30 degrees between the nearest x-axis and the terminal arm. And hopefully you're catching on that I could actually make 4 different reference angles of 30 degrees. So I could go right there. That has a reference angle of 30 degrees, nearest x-axis, and the terminal arm is 30 degrees. And I could also do one over here, 30 degrees, like that. Nearest x-axis and the terminal arm is 30 degrees. So when you get given a reference angle, it actually could be in any of these spots. Then we need to talk about standard position angles because all of those spots have different standard position angles. Remember that a standard position angle is from the positive x-axis counterclockwise to the terminal arm. So for instance, with this blue one, my standard position angle would be from the x-axis counterclockwise all the way to the terminal arm, like that. So it would be that massive angle. That's almost a full circle. In fact, it's 330 degrees is the standard position angle to get to that spot. And every one of these arms has a different standard position angle. If I look at the red one has a standard position angle that goes to here, which would be 180 degrees plus 30. So that would be 100 or 210 degrees. The green one would be from the positive x-axis all the way to the green line. That would be 150 degrees. And then the pink one right here would have a standard position angle that's the same. It's also 30 degrees. It's the same as the reference angle. So we need to make sure that we have our definitions straight. Reference angle goes to the nearest x-axis. Standard position angle tells you more information because it comes from the positive x-axis counterclockwise. And if you're wondering where I was getting those numbers and stuff, don't worry too much about that. I'll show you a couple questions. We're going to do some calculations so you can see. As long as we understand reference angle is the nearest x-axis, standard position angle is the positive x-axis. Okay. Let's look here. So find the standard position angle for the four angles below. Each diagram has a reference angle of 35 degrees. Awesome. For this one, the reference angle and the standard position angle are the same thing in the first quadrant. They're both 35 degrees. Let's talk about this one right below. If I want to find the standard position angle, first let's draw the standard position angle. The standard position angle is from the positive x-axis counterclockwise until you hit the terminal arm. That red angle that I just drew, that is the standard position angle. To calculate that angle, you need to remember a few spots on your graph. So the first thing you need to realize is that from this axis to this axis would be 90 degrees. From that axis all the way around to here, if we did that full spin all the way to there, that would be 180 degrees. So if I wanted to figure out the angle from here all the way to there plus that 35 degrees, then what I would need to do is I need to do 180 degrees because that would get me to here, and then plus 35 degrees to tell me that my standard position angle is 215 degrees. That's how I was getting those calculations on the other slide too. Right? I was doing those tricks. We have a couple more. So if we look at this one, if we want to find the standard position angle, the mistake that people make is they realize, okay, that's the standard position angle. And then they try to do something with the fact that from here to here is 90 degrees. They'd be like, oh, 90 plus 35 would give me that standard position angle. But that's not true. The reason it's not true is because this 35 degrees is a reference angle, and reference angles go to the nearest x-axis. They're telling you that that gap right there is 35. So what we need to do is we need to go all the way to 180, which would be to there, and then subtract away this part to give us our standard position angle. So if we went 180 degrees and we subtracted 35 degrees, that would give us 145 degrees. That is the standard position angle for that shape or that terminal arm. All right, last one down here. To figure out this standard position angle, I would draw from here all the way around to there. That's our standard position angle. The way we're going to do this one is we're going to realize that if we had gone all the way around in a full circle, like that would have been 360 degrees. But we didn't do a full circle. We did a full circle minus this part right here. And that angle was 35 degrees. So I need to go 360 degrees minus 35 degrees, and that will tell me that my standard position angle for that question is 325 degrees. So all those questions had the same reference angle, but very different standard position angles. That's why it's very important to know which type of angle they're talking about in a question. Are they talking about standard position or are they talking about reference? Awesome. We have 3 questions right here. I want you to try to draw these standard position angles and then also draw the reference angle. You're going to draw these things in these boxes. So for instance, this box right here, there's my y-axis, there's my x-axis. You try to draw it in there. And I'm just going to add those lines for all of these. So x-axis or y-axis, x-axis, and so on and so forth. Y-axis right there, x-axis right there. So go ahead, try to draw these reference angles and the standard position angle. They're giving you standard position angles right now. Try to draw them out. All right, hopefully you gave that a shot. Let's do the first one. The first one is an angle of 155 degrees. If I was to do that, I take my line. Standard position angles always start at the x-axis and go counterclockwise. If I put that line to here, this would be 90. If I put it to here, that would be 180. I want to be somewhere in between 90 and 180, about halfway in between. That would be a good spot for my terminal arm, making this my standard position angle of 155 degrees. That is in quadrant 2. And it has a reference angle in here of 180 degrees minus 155. That would tell me the reference angle. In this case, it's 25 degrees. The reason I did 180 is because 180 would get me all the way here. Then I subtract away 155, so I'm getting rid of that part of it. Oh, God. Everything just disappeared. Oh, no, oh, no, oh, no, oh, no. There we go. Ain't nothing I can't fix. Tell you that. Tell you that for free. All right, let's try this question. For angle 235. So if you were to try to draw this, terminal arm starts on the x-axis and goes counterclockwise. If I drew my line here, that would be 90. If I drew it here, it would be 180. If I drew it here, it would be 270. We're trying to do 235. So I should be somewhere in between 180 and 270. So somewhere in here. Let's just draw it like that. And then we do a good job labeling it. We would say this right here is 235 degrees. And it is in quadrant 3. The reference angle in this question is this spot in here to the nearest x-axis. If I know that this would be 180 degrees to there. Oh, sorry. Then I need to go 235 and subtract away 180. And that would tell me that missing spot in the middle, which is 55 degrees. Those are two terrible 55s. Holy Toledo's. No wonder I can't do Pythagorean theorem yesterday. There we go. This one, 310 degrees. So again, start here. This is 90, 180, 270, 360. We don't want to get all the way to 360, so we go about there, and we call that angle like that. We call that 310 degrees. The reference angle is this angle in here. To calculate that angle, we would go 360 degrees, which would be a whole circle, and we subtract away the 310 degrees that got us almost all the way there to get the missing chunk, which is 50 degrees. Oh, and that's in quadrant 4. Ta-da! How beautiful is that, hey? All right. This question. Determine the angle and standard position in the second quadrant that has a reference angle of 100 or of 48. So this is a multiple choice question. So take a minute, pause the video, see if you can get the answer A, B, C, or D. All right, to do this question, we're going to imagine a Cartesian plane. And we're going to put what they said happened. They said they have determine the standard position angle. So we're looking for standard position. In the second quadrant, okay, so I have a line that goes into quadrant 2 that has a reference angle of 48. Reference angles are in here, 48 degrees. This question said, determine the standard position angle. So determine this. To figure that out, we would go 180 degrees because that is what would get me all the way to here. And then we're going to subtract away that 48 to be left with our standard position angle, which would be 132 degrees. C was your answer. Cool. Standard position angles, we always go clockwise. Technically, you can go counterclockwise. So it is possible that when you're building a terminal arm, you know how I always say you go positive like this? You technically can go the other way too, like this. If you go the other direction, then you're doing negative angles. So for instance, this line that they've drawn out here went backwards. And I know it went backwards because of how they drew the standard position angle. They drew it backwards. So instead of it being 160 degrees, it's negative 160 degrees. To figure out the reference angle for this, the reference angle would be right here. To figure out that gap, we would realize 180 degrees would have got us all the way backwards to here. If we subtract away that 160, I would be just left with that standard position angle, that reference angle, which is 20 degrees. Like that. If you wanted to figure out a coterminal angle, or the positive standard position angle, then you need to imagine you went the other way like this. If you want to imagine that, you try to figure out what number would get me from here to there. To do that, I'm going to go, well, this would have been 180, and then I have to go 20 more. So 180 plus 20 would get me 200 degrees as the positive standard position angle. Notice they both got you to the same spot, right? Because they got you to the same spot, that means 200 degrees and negative 160 degrees are coterminal angles. They get you to the same spot. It's just one rotated positively, which is counterclockwise, one rotated negatively, which was clockwise. But they got you to the same spot. Cool. We're going to draw a few of these reference angles that are negative, or standard position angles that are negative. And then we're also going to find the reference angles. So this first one, they're telling me that the standard position angle of this first one is negative 45. That means they started on the positive x-axis and they went backwards 45 degrees. If they went to here, that would be backwards 90 degrees. We want to do backwards 45 degrees like that. This is negative 45 degree standard position. If you wanted to determine the reference angle is the angle from the line to the nearest x-axis. In this case, it's the same number, it's 45 degrees, but notice that it's positive. Reference angles are always positive. It doesn't matter what direction they go. The standard position angles can go backwards, and that's fine. Reference angles are always positive. Awesome. If we look at B, so for B, they've gone backwards 150 degrees. So if you started here and you rotated backwards, this would be 90 degrees. This would be 180. We want to go negative 150, which is right about there. This is negative 150 degrees. To find the reference angle is in between the x-axis and the terminal arm. This would be 180 degrees. Subtract away 150 degrees to get 30 degrees as your reference angle. Again, notice that reference angles are always positive. Down here, we're going backwards 210. So this would be 90, 180, 270. We don't want to go all the way to negative 270. We want to do negative 210. So we'll be somewhere like that. That means this is negative 210 degrees. To figure out the reference angle, which is from the nearest x-axis to the line, that would be 210 degrees, subtract away 180 degrees to give me a total of 30 degrees. And the last one, if we did negative 300, that means I'm going backwards because it's negative. This is 90, 180, 270, and I just want to go a bit past 270 like that. That makes this negative 300 degrees. The reference angle is from the arm to the nearest x-axis. That's the reference angle, and that would be 60 degrees. I got that by doing 360 degrees, subtract away that 300 degrees that we had, and it gives you the missing portion. Fantastic. Now that we've kind of reviewed our reference angle, standard position angle, and we've talked about now going in other quadrants, we've talked about positive angles, negative angles, so on and so forth, we're going to start building triangles again. We're going to skip this slide, and we're just going to get right into it and get into some discussion about triangles and stuff like that. So this says for each angle alpha is in standard position, state the coordinates which the terminal arm could lie. All right. We learned this stuff yesterday. We learned that when you get given ratios, like for instance, you get given the sine ratio, you're actually being given some information. That information you're being given is your opposite over your hypotenuse for the sine ratio. And we know that when we build triangles, your opposite side is your y, and your hypotenuse side we call r. All right, we learned that yesterday. Right, we have these ratios; they're actually coordinates, and they're actually more information than it seems. So when they give you a ratio, like they gave us right here, and they said sine of alpha equals 4 over 5, they actually gave us some information. They gave us a y value, and they gave us an r value. Therefore, we can now build what this ratio is looking like. To build it, we draw our little graph, and then we say, okay, this has a y value of 4 and an r value of 5. So if I was to draw it like this, that triangle has an r value of 5 and a y value of 4. And this in here is alpha. That's me trying to draw an angle alpha. Try again. Yeah, we'll go with that. That's what we learned the other day, right? These ratios, they mean more than they seem. All right. Yesterday, we always stuck to quadrant 1, when in reality, this triangle might not be in quadrant 1. The reason it might not be in quadrant 1 is because there's more than one spot that y could equal 4. For instance, I could draw this exact same triangle, but over here. And I could still have in this triangle a y value of 4 and an r value of 5. And this right here could still be alpha. That means that this ratio could be in quadrant 1 or 2. And because we have no other information about this ratio, then we have to accept both answers. We don't know which quadrant it's in. All we know is the y value and the r value. Well, those triangles both have y of 4 and r of 5. Therefore, both triangles are legitimate triangles. Every time, starting today, that you get a ratio, you need to consider all coordinates it could be built in. So when I look at this right here, this is the Cos ratio. We know from yesterday's lesson that the Cos ratio is the adjacent over the hypotenuse, which is our x over our r. So when they gave us a Cos ratio, they gave us an x value of -1 and an r value of 2. If we wanted to sketch that, let's try sketching it. The first triangle I could build like this. And that triangle has an r value of 2, and the x value has gone -1. Right? Negative goes to the left. But I could also draw this triangle like this. The reason that triangle also works is because it has the same x value of -1, and now the r value is just going down like that. Both of those have the same ratio. They both have an x value of -1 and an r value of +2. Therefore, this ratio could be drawn in quadrant 2 or quadrant 3. And both answers are acceptable. Awesome. Let's look over here at C. For C, we have tan equals 1 over 5. We know from yesterday, I'll write it up here, that tan of an angle equals opposite over adjacent. Opposite is your y, adjacent is your x. So they have told you that you have a y value and an x value of 1 over 5. Oh, sorry, that's a y and an x. Sketching this one's probably the hardest one to sketch. So if we sketch it, an x value of 5 means I went to the right. A y value of 1 means I went up. So I could draw this triangle right here. And that has a y value of 1, an x value of 5. Cool. Here's the tricky part. With tangents, because you have y and x, it is possible that you actually had negative 1 over negative 5. And those two negatives might have canceled each other out to leave you with 1 over 5. So that means this triangle could have been built back here, where I have a negative 5 as my x value and a negative 1 as my y value. I've gone left and down. Both those triangles are legitimate because they both would simplify to be 1 over 5. Therefore, this could be built in quadrant 1 or 3. Awesome. Give D a shot on your own. If you did this one on your own, sine is y over r. That means to draw this thing, it's y is negative 5, so that means I've gone down. So I could go like this, because that would have a y value of negative root 5 and an r value of positive 5. The other triangle I could have built would look like this. That thing has a y value of negative root 5 and an r value of positive 5. So this could be quadrant 3 or 4. Just to make, sometimes people get a little bit confused, especially with that last one, because the negative is in front, and they say, well, I don't know if the negative goes to the y or if the negative goes to the r. Just to make things clear, r is always a positive number. R represents the distance from the origin to the end of the line. Distances are always going to be positive for us. The x and the y values represent moving left or right or up or down, which is why they can have negative values, because negative means left or down. But r is an actual distance that you're calculating, so it will always be positive because we measure distances positively. Sometimes we measure them negatively if we're in a bad mood, but I try to be positive mood, so then I always measure positively. That's the worst. That might be it. What's the date today? January 5th. I'm doing this on Tuesday night. That might be the worst joke I've ever told right there. So mark that in your calendar. January 5th, 2021. Worst joke ever told. I apologize. That was brutal. All right. These next two questions are kind of they're just review questions from the other day. feel free to give them a shot. The only trick is that when you're done and they ask you to find the measure of theta, theta is in standard position. So see if you can find the angle in standard position. You'll have to find the reference angle using SOHCAHTOA and then find that theta position. I'll put the answers up so you can see the answers, but you just try both questions on your own. Good luck. All right, so there is your first answer. So you can check your work quickly. A couple things to note. First thing, make sure that you did Pythagorean theorem properly. -5 squared is 25. If you don't put brackets, your calculator does it wrong. So make sure that you put brackets. Next thing is at the very end, when you're measuring your angle, make sure you do cos. Now, sometimes it won't matter which one you do, but when you start to go into other quadrants, do whichever ratio is positive. So sine was negative, tangent was negative. I want to try to avoid negative numbers. They do weird things in my calculator. So I did cos as my ratio. When I did cos, it gives me this angle of 68 degrees. That 68 degrees is inside the triangle. The question then said, determine the measure of theta. Theta is in standard position, which is this red angle I've drawn on the outside. So I need to do 360 minus that 68 degrees to get 292. Awesome. You can try this one on your own. All right, and there are all your answers for that second question. Hopefully you got it all right. If you didn't, feel free to pop in and ask me some questions and for some help. Cool. Tomorrow we'll continue on with this idea of building triangles in different spots. And it'll be a blast. Trust me. All right. Take care. See you soon.